Hello, Professor Simmons here. In this video, we'll look at separation of variables for a differential equation that involves time as well as space, and the situation we're looking at will also involve Bessel functions. In short, we're looking at the case of a circular drumhead that is vibrating. Now, because the drumhead is vibrating, that means the differential equation we're looking at is the wave equation. Because the drumhead is circular, then the spatial variables it makes most sense to use are those of plane polar coordinates. Let's call the displacement of the drum membrane vertically up or down from its rest position by the name f. So then f is a function of radius, angle, and time. And because the drumhead is vibrating, the displacement obeys the wave equation. So the spatial derivatives on one side of the equation, the time derivatives on the other, and a factor of 1 over velocity squared relating them, and that's the velocity associated with the vibrations. So remember that the drum membrane is circular and it's fixed at the edge, meaning that there is no displacement of the drum membrane out at the edge at the radius r equals d that corresponds to the radius of the drum itself. That will be important when we're talking about the form of the solution in the end. For now, let's try to do the separation of variables, and we'll begin by trying to separate the space from the time variables. So we'll make the ansatz that our displacement function f separates into a spatial part psi, depending only on radius and angle, and a time piece t, depending only on the time coordinate. If we substitute this into our wave equation, the wave equation takes on this form. And we see here, let me just remind you, so the space derivatives, of course, apply only to psi, because t only depends on time. And the time derivatives only impact the t function, where, just a point of notation, the dots represent time derivatives. That's just a convention that's widely used in physics that we will adopt here. If we now divide this equation through by the full displacement function, we see that we've now achieved separation in that we have functions of space only on the left side, functions of time only here, and therefore the only way that they can be equal to one another for all space, for all time, is if each term is in fact equal to a separation constant, which we'll call negative k squared. So that's the first separation constant in our separation. On the next slide, we'll proceed with the separation. So let's go there. So here we are with the equation we were just looking at, where we've achieved the first separation constant. Let's use the middle term and the right-hand term now to address the time part of the solution of the wave equation. We see that this piece of the equation can be written in this form, where it's clearly an oscillator equation. And the solution is simply in terms of cosines and sines. And we note that this k times v must actually be, in combination, a frequency variable with dimensions of 1 over time. Keep in mind that as we continue to use this frequency variable omega, that it is proportional to our separation constant k. Now that we've figured out what's going on with time, let's go back to the spatial part of the wave equation. So looking at the, going back to our separated equation and replacing the time part now using the separation constant, we see that the spatial equation becomes the Helmholtz equation. We've got space derivatives of our spatial variable psi, and then we have a k squared psi term as well. If we want to write out the del squared explicitly in terms of derivatives with respect to r and theta, we see that this is taking on a nearly familiar term, form, something that we've seen before, and in fact we can separate this by taking our overall space variable psi to be the product of a function of r only and a function of theta only. If we make that substitution and then multiply the overall equation by this factor of coordinate r squared divided by the spatial variable, suddenly our Helmholtz equation takes on this form, and we see that we have terms depending on r only, one term depending on theta only, another r term. And so once again we say, the only way that all the r terms and the theta term can actually cancel one another out to be 0 for all radii for all values of angle is if they separately each equal another separation constant. So this angular term equals our second separation constant, which we give the name negative m squared. Now on the next slide, we'll finish the separation of the spatial part. So to finish the separation of the Helmholtz equation now, let's look at the angular piece, the part that we were just looking at the end of the last slide. And we see that we have the angular equation is simply that two angular derivatives of the angular function theta equals the angular function times that separation constant, negative m squared. But this is an oscillator equation again, and so we know that the form of the function that satisfies it is again cosines and sines that depend on that separation constant. The last step is then to look at the form of the radial equation. To do that, we multiply our Helmholtz equation through by r again, and we obtain this equation here where there's a 2 derivative term, there's a 1 derivative term, and then there's a no derivative term containing one piece involving the second separation constant that used to be the angular part of the overall equation. And then there's a term here depending on the first separation constant, which is the piece that used to depend on the time part of the equation. This purely radial equation is in fact Bessel's equation again. So we know that the solutions to it are potentially the Bessel functions and Neumann functions. However, physically, the Neumann functions don't make much sense here because the center of the drum is never going to displace itself down infinitely far below the equilibrium point of the drum. So only the Bessel functions really make sense as radial solutions. So the entire form of our function describing the displacement of the drum membrane then is the sum of terms that depend separately on the three variables. There's a product of the Bessel function times the oscillation frequency part here from the temporal part of the equation times the angular part here. We note that the angular part of the solution depends on the second separation constant, whereas the radial and time parts each depend explicitly on the first separation constant. Here there's an explicit factor of k, and here, remember, omega, this frequency, is actually proportional to k. Finally, remember that the values of the separation constant k that are going to be physically part of the solution are the ones that ensure that the displacement of the membrane will actually vanish at the outer edge of the drum, meaning the k's that make our Bessel function vanish when r is equal to d. So those are the special values of this separation constant that actually enter into the solution. So in other words, Bessel function zeros are crucially important to the form of the solution. And we'll talk about more of that in class. That's all.